All right, so in this video, we're going to take a look at finding the curvature of a circle and then take that concept and extend it into an oscillating circle as well. So the formula that we're going to use here was one that I pointed out in the last video. We're going to use kappa equals the absolute value of x prime y double prime minus y prime x double prime, and that's all going to be over x prime squared plus y prime squared, and that denominator raised to the 3/2 power. Okay, now it looks a lot messier than it's really going to be, fortunately. So I'm just come over here to the side here and go through the x prime, x double prime, stuff like that. So x is going to be the a cosine t. So then the x prime is going to be negative a sine t, and x double prime is going to be negative a cosine t. Y is going to be a sine t, therefore y prime is going to be a cosine t, and y double prime is going to be negative a sine t. All right, so now I'm just going to take that stuff and plug it in. So kappa is going to equal my x prime, y double prime, this guy here and this guy here would give me an a squared sine squared. So that would be an a squared sine squared t minus, and then y prime x double prime would be an a squared cosine squared with that negative. So that's going to be a plus a squared cosine squared. And you can put the absolute value bars on there. And then down here, x prime squared would be a squared sine squared, a squared sine squared. And then for y prime squared, that would be a squared cosine squared. And then that's going to be raised to the 3/2 power. All right, so from here, quite a bit of stuff can happen. You can see the a squared can be factored out. If the a squared is factored out, that's going to give us sine squared plus cosine squared, which is 1. So currently we have kappa now equals the absolute value of a squared, which again is positive already. And then in the denominator, similar things happen. You can take the a squared out, sine squared and cosine squared give you the 1, but we're still going to have the a squared raised to the 3/2 power. So that's going to be a squared raised to the 3/2 power. So then kappa, we've got our a squared on top, and in the denominator, that's going to be an a cubed, which is going to be 1 over a. Now, what is the a? Well, if you come back up here and you look at the parameterization, this is a circle of radius a. So the conclusion that we can draw from this is that the curvature of a circle is always constant at 1 over its radius. And that makes sense that it should be constant. You're not going to get that slope predictor or the curvature predictor idea like we talked about. It's always going to be constant on a circle, and it happens to be 1 over its radius. Okay, so now we're ready to talk about the oscillating circle. An easiest way to describe this is to kind of go back to Calc 1 and remember that when we find the equation of a tangent line to a curve at a point, the instantaneous rate of change on that curve is equal to the slope of the line at that point. And this is similar in the sense that the curvature of our curve C is going to equal the curvature of this circle at this point. Okay, so it's kind of like the perfect circle that's going to fit right along in there and have the same curvature at that point. Okay, so now to come up with this, it's actually pretty interesting. If you'll remember, for an equation of a circle, you'll need two things. You always need the center, and you always need the radius. Well, the radius we've already talked about. We know that the curvature is going to be 1 over the radius, which means that the radius is going to be 1 over the curvature, kappa. So that one's pretty straightforward. But now coming up with this center, we have to be, again, a little bit creative. So what I'm going to do is I'm going to start by acknowledging that this position vector right here, that's going to give us the position of the particle along this curve at any point, specifically in this case at t naught, is pointing right here. All right, now at that same point, I'm going to go ahead and construct a unit tangent. Okay, so we would know at this point how to construct a unit tangent, and so that would look something like this right here. So I'll call that our unit tangent. All right, now from our unit tangent, we could construct a unit normal. So the unit normal would be coming up like this. So I'll call that the unit normal. Now, the unit normal is not the radius of our circle, but because it is a circle, it is going to point in the direction of that center. So what we're going to need to do then is we're just going to need to lengthen the unit normal. And remember, it's a unit vector, so it's as simple as multiplying by whatever the length is we need. So then we would lengthen this. So that would be some scalar times the unit normal. Now the reason why that's important is because this vector right here, which is pointing directly at our center, is actually going to be the sum of this vector plus this vector right here. All right, so I'm going to go ahead and put an example up here real quick. The example we're going to look at is going to be find the oscillating circle on the curve y equals x squared at the point 1, 1. Okay, so to get this thing started, I would probably start with the radius first. Remember, the radius is going to be 1 over the curvature right here. So for curvature, the formula that I'd like to use in this case is going to be one that we saw in the previous video. The absolute value of y double prime divided by 1 plus y prime squared, and that's again raised to the 3 halves. So in this case, it's pretty straightforward. If our y is x squared, our y prime is 2x, our y double prime is going to be 2. So then kappa is going to equal 2 over 1 plus, that would be then a 4x squared, all raised to the 3 halves. So this y prime is 2x. When I square it, gives me a 4x squared. So this is the curvature predictor, if you will. I would evaluate this now at x equals 1. I say x equals 1 because of this right here. And that gives me now the curvature of 2 over 5 to the 3 halves. Now that means our radius is going to be 5 to the 3 halves over 2. And I say that because our radius is going to be 1 over our curvature, so I just flip that thing around. Okay, so we box that in. We'll come back to that here in a minute. Now we need to worry about coming up with that center. So to come up with the center, I'm going to go ahead and start by saying let x equal t and y equals t squared. Now what I've really just done here is parameterized, and that way we can come up with our vectored valued function, t and t squared. So again, I just parameterized this right here, and then we went into our vector valued function form. So the first thing I'm going to look for now is going to be the unit tangent. And so the unit tangent would be the derivative of this divided by the magnitude of its derivative. So it looks like t, the unit tangent, would have a 1 and a 2t divided by the square root of 1 plus 4t squared. And we can clean that up a little bit here. That's just going to be a 1 over the square root of 1 plus 4t squared, and then 2t over the square root of 1 plus 4t squared. We would evaluate that at t equals 1. And I know that it would be t equals 1 because if our x is equal to 1, or our x is equal to t, then we would have to evaluate it t equals 1. Okay? So if we do so, that's going to give us a unit tangent of 1 over the square root of 5 and 2 over the square root of 5. Okay? So we've got our unit tangent. Now, this is where I'm going to let you guys use a little bit of a trick. We've done enough problems now to know that finding the unit normal can be a little bit challenging, to say the least. So what I would encourage you to do is just think outside the box a little bit here. We know that this vector t and this vector n are going to be orthogonal. They're going to be perpendicular. And just like we saw in an earlier assignment, if I take those two vectors and dot them, they should equal 0, right? So I know that t dotted with n is going to equal 0. Well, I already know what t is. T is going to be this guy right here. So I need to come up with a vector that if I dot it with this, I'm going to get a 0. Okay? So follow me here. If I have a 1 over square root of 5 and a 2 over square root of 5, the easiest thing to dot it with and come up with a 0 would be me just flip-flopping these two things and making one of them negative. So if I put a 2 over root 5 and a 1 over root 5, and hypothetically make this one negative, you can see that this guy times this guy plus this guy times this guy would in fact give me a 0. But I just randomly put that there. I've got to make sure it's in the correct spot. Well, the unit normal is always going to point inward, okay? Technically, you have a unit normal that could go this way, but the unit normal will always point inward. So I want to pick the negative sign. I want to put the negative in the correct spot so that it's going to point inward. So what I might do here now is I might go ahead and draw a picture to see exactly what it is that I'm trying to come up with. So my picture looks something like this. Here's my parabola right here. Here's 1. And so that circle that I'm studying is going to be this guy right here, where this would be the unit normal that I wanted. And that unit normal would then need to have a negative, I put the negative right here, a negative first coordinate. So I'll move negative then up, which would be this guy here. So I've assigned the negative right there, still noting that if I do dot these, I get 0. And that gives me then confidence knowing that the unit normal that I want would be negative 2 over root 5 and 1 over root 5. So there's that unit normal that I've been searching for. And in this case, in context, we're able to come up with it a little bit more creative. Okay, so now that we have all of the stuff that we need, what are we going to do with it? Well, remember, the goal here was to get the center. And that center was going to be this guy right here, which can be found by adding this and this. So the first part here, the vector r evaluated at our point, that's going to be this guy evaluated at 1. So we have 1, 1. So this black vector here is 1, 1. And I need to add to it the scalar multiple of the unit normal. So the unit normal that we found was the negative 2 over root 5 and 1 over root 5. The scalar that we need to put out here that's going to lengthen this unit vector is actually going to be the radius itself, right? From here to here is going to be the radius. So I'm going to need to drop in this 5 to the 3/2 over 2 out in front of that. When you run through this arithmetic, we end up with the vector negative 4, 7/2. So that vector right there is going to be the one that points us to our center, meaning that we have a terminal point at negative 4, 7/2. All right, so when all's said and done here, we can put it all together now. We know that x plus 4 squared plus a y minus 7/2 squared is going to equal the radius squared. And if I square that radius, that's going to give me a 125 on top and a 4 on bottom. So 125 over 4. So there's the equation of the oscillating circle. And I've got this very, very informal picture up here, but that blue circle right there, that's the one that you've just found. I would encourage you guys to graph that. You can go to Desmos, take a look and see what you found. But it's pretty interesting that at this point right here at 1, 1, the curvature of our parabola matches the curvature of our circle.